Pythagorean triples. The earliest known evidence of Pythagorean triples is contained in a Babylonian clay tablet written about 1800 BC. This tablet was named Plimpton 322. The tablet contains a table with 4 columns and 15 rows. The contents have been identified as what we call Pythagorean triples. In the Elements, Euclid collected, organized, and proved geometric ideas that were already used as applied techniques. Geometry as we know it has its roots stemming back to Euclid. Today we refer to it as Euclidean geometry. So what is a Pythagorean triple? A Pythagorean triple occurs when we restrict all 3 side lengths of a right triangle to be of an integer length that satisfies the Pythagorean theorem a squared plus b squared is equal to c squared, with the condition that a is greater than 0, b is greater than a, and c is greater than b. Pythagorean triples get their name from the Pythagorean theorem because they are a specific result of the Pythagorean theorem. How can we find a Pythagorean triple? We can thank Euclid for a general formula which produces Pythagorean triples. Omitting his proof for time's sake, from the Pythagorean theorem, he found that a Pythagorean triple, a, b, and c, is equal to, for a, m squared minus n squared, for b, 2mn, for c, m squared plus n squared, where m is greater than n and n is greater than 0. And m and n are integers, with an additional condition that m and n are of opposite parity, which is to say that m and n are both not even, or that they are both not odd. So let's consider an example to help illustrate what we know so far. If m is equal to 2, then n is equal to 1. This produces the Pythagorean triple 3, 4, 5. One may ask, how many Pythagorean triples are there? One can argue that the set of Pythagorean triples can be placed in a one-to-one correspondence with the set of natural numbers, which shows that the set of all Pythagorean triples is countably infinite. Thus, there are an infinite many possible Pythagorean triples. Does Euclid's formulation capture all possible Pythagorean triples? No. Consider the Pythagorean triple 9, 12, 15, which is equal to 81 plus the 144, which is 225, which is the 15 squared. But there is no such m and m which creates this triple. Wait a second, let's not be so hasty. From earlier, we saw that when m is 2 and n is 1, the result is a Pythagorean triple of 3, 4, 5. If we scale a, b, and c in the 3, 4, 5 triple by a factor of 3, we find the 9, 12, 15 triple, missed by Euclid's formulation. Euclid's formulation of the Pythagorean triples are primitive Pythagorean triples. A primitive Pythagorean triple, a, b, and c, exists if the following three conditions are true. 1, if the greatest common divisor of m and n is 1, or we could also say the same way that is referred to as m and n are relatively prime. 2, if m and n are integers where m is greater than n and n is greater than 0. And the third condition, if m and n have opposite parity, which is one is even and the other is odd. If k is an integer such that k is a divisor of a, and k is a divisor of b, and k is a divisor of c, then the Pythagorean triple ABC is a non-primitive triple. An update to Euclid's formulation will now capture all possible Pythagorean triples when it's expressed as A is equal to K times the quantity of m squared minus n squared, and B is equal to K times the quantity of twice the product of m and n, and C is equal to K times the quantity of m squared plus n squared, for some integer k being greater than 0. Is this useful to know? Why would a teacher want to know about Pythagorean triples? Well, I believe knowing how to generate Pythagorean triples can assist educators in creating and understanding geometric problems with right triangles of integer side lengths.